Hi everyone. Thanks for continuing to join along in our introduction to R and how we can use it for finance and financial data. What we're going to discuss today is what I like to consider a basic introduction to just the general data structures that you'll encounter in R formatted data. So as I mentioned before, R is an object-oriented programming language. So what that means is we have objects within R that we manipulate in very specific ways that each has its own special types of attributes. Now, if you program in Python or Stata, SAS, other languages, every language is going to have its own quirks, and R is no different. However, if you're familiar with just some of these basics, then your life will be a lot easier whenever you start to mess with actual real life data. With that said, this is not meant to be a thorough introduction. It's just going to be a basic overview of things that we'll see as we move forward in this introduction or in this series. And it's also meant to highlight just the basic data structures that you'll see with real life data. With that said, let's just jump straight in. So, first thing that I want to reiterate is that R is an object oriented programming language. In this script, we're not going to deal with um, any data sets. We're not going to deal with any packages. We're just going to focus on the objects, the broad objects themselves. Now, let's start with the basics. Now, if you were to break down all data in R into three different categories, you could break them up into numeric data, string data, and logical data. Now, numeric data is exactly what it sounds like. It's whenever you assign a number to an object. Like if I were to say the number or the object called number equals 1, you can look over here in the environment and see that the object named number equals a value of 1. What that means is I can now manipulate and perform functions on this object if it allows numeric data. So I could say something like number plus 1, which is the same thing as saying 1 plus 1 equals 2. Alternatively, you have strings. Strings are character data, which are going to be referenced, or they're going to be represented and input using quotations. So I could call an object string and assign it the character data 1. And now notice over here in the environment, the object string has a character representation of 1 in quotations. But notice what happens. If I say string plus 1, it's an error, which makes sense because string is a character data format, so you can't add 1 to a character, right? Which makes sense intuitively. And a third major category, which is super important to take note of, is a logical format. Right, and sorry if you hear my dogs in the background right now. They are getting a little heated over something, and I'm not entirely sure what the reason is. Um, but if you just bear with me 1 second, they'll calm down. Let's focus on R and focusing on this idea of a logical data structure. It's going to take one of two values. It's either going to be true or false. And this is going to be important in some cases. Honestly, in my experience, only time that these have come into play are typically with government data, where they um, instead of representing binary data as zeros and ones, they may represent it as trues and false. Now, what if we wanted to build up? If instead of having just individual objects that are assigned an individual value, what if we try to combine data? Well, R can do that too. That's where this idea of vectors, lists, and matrices come into play. You can have vectors that are numeric, you can have vectors that are strings, You can have matrices that are numeric, and you can also stitch together all of these different data types. It's like a vector, a numeric vector is going to be a collection of numeric data. Like if I call one object vector num, vector underscore num, and if I wanted to stitch together or collect individual elements into a single object, I could say equals C and then 1 comma 2 comma 3. And now this is a vector that is also numeric, which means I can perform mathematical operations on this. So if I were to say vector num plus 1, all of the individual elements within my vector have now been manipulated by the units, right, by value of 1. Or I could also say something like 2 times vector num, and now everything has been scaled by a value of 2. I can also make a vector of strings, which, as you might expect, all the individual elements within a vector of strings is going to be strings, right? However, what do you think happens when, if I wanted to combine, let's say, the numeric and string data? Call it maybe vector combine and say C equals 1, 2, and 3. You can do that, but what do you think is going to happen? Let's call it. Now notice R defaults all the data to string now. Even though I told it a numeric 2 and a numeric 3, because there's a character string, it forces everything to be a string as well. That's where lists come into play. Lists are R's way of allowing you to embed many different data types within a single object. So let's say I wanted to put a logical string in there, not a logical string. Let's say I wanted to put in a character string, a vector of numbers, and a vector of strings. Well, I can say list, and call my object string, my vectors of numbers, and my vector of strings. And now if I run this code using Control Enter or Command Return, whatever program you're in, notice my first sub-element of list data is the character string 1, which is something that we defined in line 7. But now I have a vector of numbers within my second element of list, and my third element is a vector of 3 character strings. So lists are powerful, not used so commonly anymore in my own experience, but they are still very helpful ways to combine data and represent it efficiently. And then you have matrices. Matrices are, think of it as a spreadsheet of just numeric data. It takes data that you feed it using the C operator, or if you have a data frame of purely numeric data, you can also convert it to a matrix and vice versa. And you can tell R how many rows you want, how many columns you want, and if you wanted to distribute your data by row or by column. Personally, I like to use by row because that's the way I think. However, I know people that like to go by column as well. And if you want to say by column, you would say by row equals false. So what this is going to do is put the numeric data 1, 2, and 3 on its own row, and 4, 5, and 6 on its own row. If I run this, and now if I want to present matrix data, we can look down here in the console, and you see 2 unique rows of the numbers 1 through 6 distributed by row using standard matrix notation, where row 1, column 1 is a value of 1, row 1, column 2 is a value of 2, and so on and so forth. Matrices are once again not used very much anymore because data frames have taken their place, and I'll show you that here now. Well, in order to build up to a data frame, you really need rows and columns, or observations and variables, where variables are going to be your column data. And in our next video, I'll show you real-life data and how this looks. But for the time being, let me show you the two basic building blocks of data frames in base R. We have two workhorse functions called rbind and cbind. Rbind stacks rows on top of each other, and cbind stacks or puts data beside each other. So for example, if I wanted to put a vector of numbers and a vector as a string together on top of each other, I can call rbinds, and notice I have an observation of numeric data and, an observation of my 1, 2, and 3, and an observation of the strings 1, 2, and 3. However, notice, because I have strings and I stacked numeric data on top of string data, R coerces my numeric into strings. And cbinds is not going to stack on top of each other, but it's going to put side by side, because cbind is column bind and rbind is row bind. Same thing happens though with the data structures. R coerces numeric into strings. Well, let's say you don't want to just be dealing with this data out in the open. You want to store it for future use. That's where data frames come in. Think of data frames as spreadsheets in Excel, where you tell R to combine certain data and convert it to a data frame for future use. Now notice what happens. If I call my data frame DF, you could call it anything. You could call it Bob, Joe, Billy, whatever. And we have a slightly different structure now, right? Actually, let me pull it up here, where now our data looks a little cleaner. We don't have the quotes around the strings. However, on the back end, R still represents or still recognizes these as being strings within the column called vector string. And vector num is also a string column as well. However, I could change it by saying something like data frame vector num equals as numeric vector numeric. And now R is going to represent my numeric data by right aligning it and my character data by left aligning it. But let me just Control Z this so that way if our file is back to the way it was meant to be. Now with that said, as I'm starting to wrap up this video, I'm going to show you just a couple of more important things. So first is how to reference elements within a dataset, and the second is how to check data types. Both of these are super duper helpful tools when dealing with real life data. Well, because R was written by statisticians, or made for statisticians by statisticians, index notation is huge. But it's going to follow more of like the mathematical type of indexing that you may see in like a linear algebra class than you may see in Python, which is more of a computer science style of indexing. What we're going to do is, if you know the number of the elements that you're trying to see, you can put brackets around a number following the name of your objects, and R will tell you what the object or the element is within that object that matches that nth position. So here I'm telling R I want to know the value assigned to the first element within the object string, and of course it's going to be 1, the character value 1. I can do this with elements or with objects that have more than one element, like the object vector string. If I want to know the second element, it would be vector string 2. And of course, it's going to tell me the value of 2. List data, because we have data embedded within our objects, are going to follow slightly different formats. Now, the way that we're going to the way that we're going to reference list data is going to be similar to how you may reference an element within a matrix, where you're going to first reference the first element that you care about, and then the specific element within the element that you're embedded. And the way this is going to work is, actually first let me show you what happens if you just include the first item. Well, it's going to tell us the second vector that we embedded within the list. But if I include the second index, it's going to tell me the first element within the second subset of the list. So it should present the value of 1. And that's what we get. And the same thing is going to be true if we try to reference the third object within the list, where the third item within the list was our vector of strings. The first element within that list was the string called 1. Data frames follow a similar structure where you can either call an entire column or you can call an element within the spreadsheet, if you will, where the first item is going to be a row, the second is going to be the column. So if I want to see what the element within the first row, second column is, I can say df12, which corresponds to a string value of 1, or I can call a variable by following a data frame's name with a $sign, referencing the variable, and then indexing the observation. As you can see, this and the former method are equivalent. Now lastly, we have two super powerful functions, class and structure. Both of these allow you to check data types in R. So class is going to tell you that, let's say, the vector number object is numeric, and str is going to be great because you can use it on a data frame, and it's going to pretty much call the class function for every variable, every column within your data frame. Now notice if you say something like class df, it's just going to tell you it's a data frame, because class is going to look at the broad object that you're calling, whereas str is going to give you a more detailed look at your structure. But with that said, R has a lot of special structures like factors, doubles, tibbles, infinite values, NAs, not numbers, which are represented by NaNs. For our purposes in this video, I'm just going to ignore them, but they are still important. And in practice, they do make a difference. But with that said, if you have any questions, as always, feel free to shoot me an email or try to get in contact with me, and I'm happy to give you more detail. But now you know the basics of how to get into R, the basic object-oriented nature of R, and what we'll do is in the next video start manipulating and dealing with real-life data.